Hello, welcome to Schools Not Out, your daily classroom for CSEC and CAPE students. I am Karima Mundell-Thomas.
And I am Brittany Henderson. So, today we're going to be focusing on the quadratic function. Our focus for this session will be on plotting the graphs for the quadratic function and identifying the vertex, the y-intercept, and the roots. We're also going to be focusing on obtaining the solutions for the quadratic equation by factorization. Now let's get into the lesson. Let's start off with a scenario. So Emmy throws a ball up in the air from 5 meters above ground. When the ball is 2 meters from her, the ball reaches a maximum height of 9 meters and then lands back on the ground 5 meters from her. Now, what could this path possibly look like?
Very interesting question, Brittany. So I'm seeing here where Emmy throws the ball up in the air. So I'm seeing an upward movement. Then we're told that the ball reaches a maximum height. And I'm guessing we're on Earth, gravity is gonna now pull that ball down. And so I'm seeing an upward movement, a curve coming down. That's what I think that graph would look like.
Well, we'll see in a little bit.
All right.
Now, can we identify any coordinates from that scenario?
But of course.
All right, so let's look at it.
Sure.
So, we started off with Emmy throwing the ball up in the air from 5 meters above the ground.
So based on what I'm seeing here, let's shift a little for me, Brittany. What I'm seeing here is Emmy will be throwing the ball from this point right here, which based on my x value, it's 0, and based on my y value, it would be 5. So Emmy's starting point from the expression, from the situation is 0, 5.
And 0, 5, and that is correct. So that is our y-intercept. Now, when the ball is 2 meters from her, the ball reaches a maximum height of 9 meters.
So Brittany, based on that, I'm seeing here that if she started where x is 0 and it's now 2 meters away from her, we're now at x being equal to 2.
Yes.
And a maximum height of 9 meters. And so based on that, I'm seeing a coordinate of 2, 9.
All right, so that is also correct. So there we have our vertex. Now, what else happened in the situation? We had one more thing happening. When the ball lands back on the ground, it lands 5 meters away from Emmy.
So remember we said Emmy started at x equals 0. And so if it landed 5 meters away from her, based on what we have already, the ball would be landing right here at 5, 0. And that looks like our x-intercept.
Now let's look at the 3 main points that we identified. So we identified our y-intercept, our vertex, and our x-intercept. And this type of graph, or the shape of this graph, is known as a
parabola.
All right, so we have a parabola here. Now, quadratic equations are often used to model real-life situations. So it may be that we're looking at the rise and fall of profits, or the decrease or increase in the amount of time it takes to run a mile based on your age. We also know that the vertex tells us where you can find the absolute maximum or minimum cost, profit, speed, height, time, or whatever it is, for whatever it is that you're modeling. Now, let's explore GeoGebra.
So we are in our software GeoGebra, and we want to look at what these 3 variables do to our graph. So we have on screen A, we have H, and we have K. We're going to first be looking at the effect of A on this graph, and we'll tell you a little bit more about what A means as we progress. But I just want you to watch your screen carefully. So right now, A has a value of 1, and I'm going to be shifting my slider. And we're seeing here, Brittany, that this graph, first of all, it looks somewhat like a smile. So we can say We can call it a smile for now. So we're going to be talking about
a happy graph.
All right, so we'll talk about a happy graph. And that's appropriate, Brittany, because A here is positive, and so we have a happy graph. Beautiful. Now, as I'm shifting A, and it's moving now to some larger numbers, we're seeing the graph seeming to close in. Are you seeing that, Brittany?
Yes, it seems to be getting skinnier, so it's happy and skinny.
Ah, happy and skinny, I like that. All right, so we're seeing here that A actually, when it's positive, we're seeing this happy graph, and as our numbers get larger on the positive side, we're seeing the graph closing in, and as Brittany said, it's getting skinny and happy. All right, we're going to look now on the other side. What happens when our A value is negative?
Oh no, I think we have a sad graph now.
We have a sad graph. Our graph is frowning. Okay, and so A here is negative, and we're getting a sad graph that's frowning. Now, let's see if we have that same effect. So the further into the negatives that we go, we're seeing again that our graph seems to be closing in. And so, Brittany, you would say this is skinny and sad?
Yeah, it's
skinny and sad it is. All right. Now, I want to point out something here because I want to point out, first of all, so let's get on the board quickly, that our quadratic functions can be written in
vertex form.
Vertex form. So we're talking about writing it in vertex form. All right, so we mentioned A earlier.
Yes.
So this is what we were referring to just now. And we can also write it in what we call standard form. Where we have ax squared plus bx plus c. Please note that A, h, and k here are real numbers. And so A, B, and C in this form are also real numbers. Now, I wrote this here because I want us to focus a little bit on the standard form. What would happen if our A value is 0? So let's see what happens. So we're going to zoom back to the screen and see what is happening when our A value is 0. All right, so we see our graph widening, and now, so let me just see if I can. All right, so let's look at what's happening now with A being 0. Okay. How does that look, Brittany?
Well, that looks like a straight line.
It looks like a straight line. There is no curve anymore. And so I want our students to understand that with our quadratic function, our A value cannot be 0, because what would happen there, if I could go back to the board, if A becomes 0, then 0 times anything will give us 0, and so we would no longer have that x squared term, and we would basically be looking at something similar to our line.
We would be looking at a straight line.
That's right. Y equal mx plus c.
That is correct.
And so that's what we would have here. So this A value cannot be 0. So while B can be 0, C can be 0, our A value cannot be 0 for our quadratic functions. If it becomes 0 at any point, then that now gives us a straight line. All right, so we talked about vertex form earlier. We're going to just look quickly for a couple of seconds what happens. So let's change back our A quickly to a happy graph. I like our happy graph. So we're going to stick to this happy graph here. Now, what I want us to look at now is the effect that H has on our graph. So, Brittany, you're going to be telling me what you see happening to this graph. I'm moving H over into the positive numbers. What's happening to my graph?
So it looks like my happy graph is moving to the right.
Well, it looks like it's moving to my left.
To your left, my right?
It's moving to the left.
It's moving to the left.
That's right.
My right.
Oh, because you're facing that way. All right,
Yes.
so we have to do it so the viewers can understand. So my H value is getting positive, and so my graph, as I'm looking at it, is moving to the left. All right? So what's happening now as my H values, all right? So I'm over now into my negative numbers, and I'm seeing here that my graph is moving to the right. All right, so we can actually see what's happening here. So our H value is actually moving our graph horizontally. All right, so if we started with H being 0, let's just get that right there. All right, so here H is 0. We see our graph is centered on our axis. Let's look what happens when we move to the positive side of our H. Our graph is moving left. And when we move to the negative side, our graph is actually moving to the right. Now, Brittany, let us see what K does to our graph. What do you think K does before I even do it?
So if H moves our graph to the left or the right, I think K would move our graph up or down.
Well, let's test.
So let's look at.
What do you know? You're right.
Oh, look at that.
You are correct. So our K is actually moving our graph up or down. And if we look now, based on where we started, as our K values move to the right, our graph is moving up. And as our K value decreases, our graph is moving downward. All right, and I want to point out that this is called the vertex form for a reason. We mentioned earlier about vertex. And so what we're seeing here is that our H and our K values, if we look closely, they are actually giving us the vertex of the graph.
That is true.
All right.
So earlier we mentioned that the vertex is going to be our absolute maximum or absolute minimum. And we talked about our happy graph and our sad graph.
Beautiful. I'm glad you brought in max and min. So
Yes.
tell me, Brittany, when our A value is positive, what kind of graph do we have?
A minimum.
All right, so we have a happy graph, which would
Yes.
give us a minimum. Good.
So it would look something like this.
Beautiful.
So when our A is positive, we'd have a happy graph.
That's right.
And when A is negative, we would have a very sad graph, which is actually going to give us our absolute maximum.
Beautiful. I do it already.
So going back to where we started originally, we would like to find A for the parabola for the flight of Emmy's ball. So remember we started off looking at Emmy and Emmy throwing her ball?
That's right.
So now we're going to look at what the equation in vertex form would look like. Now, at the beginning, we identified 3 main points. We identified our y-intercept, our vertex, and our x-intercept. Just to remind our viewers, let us give the coordinates for those points. So my y-intercept was
0, 5.
My vertex was
2, 9.
2, 9. And my x-intercept was
5, 0.
5, 0. Now, in this case, we would like to substitute into my general form of the vertex to find what the equation would look like for this graph. So
Brittany, before you do that, based on how our curve looks, can we actually say whether A is positive or negative?
Yes, because in this case, we have a very sad graph.
Oh my, so A is
Definitely negative.
okay.
The graph is sad, unfortunately. We can also tell, so we know that A would be negative. We don't know the negative value of A just yet.
We can leave off the negative because once we calculate it, we'll reveal
find
itself.
out what A is, yes.
Yeah.
We do know what H is. Now, in this case, our graph to the left or to the right?
To the right.
To the right. So is H going to be positive or negative?
Negative.
Negative. And in this case, it would be negative. how many units to the,
2
or vertex? How many units to the
2 units.
2 units. And our K, in this case, is our graph up, vertical, or downwards.
well,
where is our graph positioned?
It's up because it's above my x-axis, so it's up.
Okay, so we have an absolute
Maximum.
So K in this case is going to be
9.
what's 9. So our ball in flight at its maximum was at 9 meters. So in vertex form, y is equal to a x minus 2 all squared plus 9. Now, in this case, as we stated before, we know that just by looking at our graph, a would be negative. Now, let us see if we could solve to find out the quantity of a. So given that we have the y-intercept, we can substitute into our equation to find the value of a.
All right, so Brittany, just to recap, remember we said that our quadratic functions can be written in standard form where we have ax squared plus bx plus c, and over here we have it in vertex form because our h and our k actually tell us the vertex, which is either the maximum if our graph is sad or the minimum. So these are the 2 forms that we're accustomed to seeing on our CSEC examinations. All right, so based on the information that we have, it's best, because we have our vertex in this situation, to use the vertex form to find out what is A.
Yes, that's so true.
Just to ensure our students are clear on what we're doing.
All right, so let us attempt to find the value of A. So using 1 point on our graph, so let us use our
y-intercept.
Let's use our y-intercept. So in this case, my x value is, when y is 5, my x is
0.
0. So I'm substituting. So x is 0. And y is
5.
So y is 5. So let us attempt to solve our equation. So 0 subtract 2 would give us?
-2.
-2. -2 all squared.
4. Once a number is squared, it's positive.
That is so correct. So we have a times 4, which is just simply 4a. So it is 4a plus 9. So 5 is equal to 4a plus 9. Now we're attempting to find what value again?
The value of a.
So we're trying to find the value of a. So we need to make a the subject of this equation.
Right, and we do that by doing inverse operations,
correct?
That
is correct as well.
Right.
So 4a is being added. We're adding
9 to 4a.
We're adding 9 to 4a.
Right.
So in this case,
we
have to do the inverse, which is subtraction.
9.
So we're subtracting 9 from each side of our equation. 5 take away 9 would give us?
-4.
So that is -4 is equal to
4a.
Because 9 subtract 9 would leave us with 0. So -4 is equal to 4a. Now a is being multiplied by 4. What is the inverse operation of multiplication?
Division.
It would be division. Remember, the aim is to get a by itself. So we're going to divide each side by 4. Now, common factor between 4 is 4. So 4 into itself will give us 1. A times 1 is A. 4 into -4 would be?
-1.
-1. So before we mentioned that we had a very sad graph.
That's right.
Right? So A is actually -1. So y is equal to -x minus 2 all squared plus k. So this would be the
We have
equation.
a value for k, remember?
Oh, sorry. Value for k is
9.
9.
Right.
So this would be the equation for
the movement
of our ball in
ball.
vertex form.
That's right.
Now, if it is that we wanted to write our equation in standard form, we would have to simply expand and simplify our equation.
Which is now in vertex form, all right?
Yes.
And so that, if it's expanded and simplified, would give us negative x squared plus 4x plus 5, all right?
All right. Now, there's one point on the graph that we mentioned earlier, the x-intercept. We can find the x-intercept by simply looking at our graph, or we can also find the x-intercept by factoring. So we could be factoring our quadratic equation.
All right, so I'm going to just clean up our board a bit.
Go ahead.
And you can guide us through the factorization.
No problem. So, in standard form, our equation is negative x squared plus 4x plus 5. As was mentioned before, A in this case is negative 1, B is 4, and C is 5. Now, let us go through how it is that we would factorize this equation. Now, we're going to use what is known as the grid method of factorization.
So we can look at our screen,
So
Brittany.
let's look at our screen.
Right.
We're going to be looking at our ax squared term and our c term. Now, let us multiply ax squared by c. Ax squared by c would give us what product?
Negative 5x squared.
So negative 5x squared. Negative 5x squared, we need to find two factors of negative 5x squared that when we multiply them, we get negative 5x squared, but when we add them, we get our b term, bx term, which is 4x. So we need two factors.
Okay, Brittany. These two factors look like 5 and negative 1.
So these factors could be 5x and
negative x.
and negative x. Now you could place these two factors anywhere in our grid, right? So the factors are going to be 5x and negative x. And we place them in either one of the vertical boxes on our grid, the blue boxes. The second step that we're going to go ahead and do is factor each row and each column. Now let's look at row 1. Negative x squared and 5x. Do they have anything in common, Karima?
Of course.
What do they have in
Immediately
common?
I look, I see x.
You see x in common.
As I look at it, that's the first thing that popped out at me.
That is correct. Now let's look at row 2. Negative x and 5. Do we have any common factors there? Do they have any factors in common?
Well, 5 is prime. And I don't see any x, so it must be 1.
Yes, it's 1x.
Okay.
Negative 1x.
Oh, negative. Oh, thank
Yes.
you. Oh, there I go again. Need to pay attention to those negative signs.
So it would be 1. Let us look
so
at
I was right.
So let's look at column 1. Negative x squared and negative x. What do we have in common?
Negative x.
Negative x. And column C, 5x and 5. What do we have in common?
5.
5.
That one is easy.
So the length of each side of our square would give us the factors of our quadratic.
Oh, that's nice.
So let us write that down. So one factor is going to be negative x plus 5 multiplied by x plus 1.
Excellent. I feel so accomplished.
You feel so accomplished, but are we done yet? When we're talking about the x-intercept, what is happening with y? So when the graph cuts our x-axis, what happens to y?
Y is equal to 0.
Y is 0. So if I wanted to find the exact points on my graph where y is 0, I would have to equate my factors to
0.
So let's find those exact points now.
Oh.
So what this simply means is that x minus x plus 5 is equal to 0, or x plus 1 is equal to 0. So let's solve again for x. So minus x is equal to negative 5.
Okay, so we subtracted 5 from
either
both sides.
sides.
Good.
So now we're multiplying x by negative 1.
Okay.
So what's the inverse of doing that? To find x by
Dividing
itself?
by negative 1.
So we're going to divide by negative 1. So x is equal to?
5.
So x is equal to 5, or x is equal to, so since we're adding 1 to x, we're going to do the inverse to get x by itself.
Which is to subtract 1.
So we're going to subtract 1 to get
From both
both sides.
That's right.
So x is equal to?
Negative 1.
Negative 1. So what this simply means, and as you could see from before, one of our intercept was actually 0, 5. And the other,
this is where the ball landed on the ground.
that's where the ball landed on the ground. The ball landed 5 feet or 5 meters away from Emmy.
Okay.
And our other solution would have been 0, negative 1. Now, if we go back to, let's go back and look at our graph for a little bit. If we notice with this graph though, would we need our second solution?
Okay, for this particular situation, so it's good that you brought that up, because sometimes when we go to the exam, we're given certain situations, and though we have 2 solutions here, there may be one solution that is not appropriate for the situation
that we're
given. So if we were finding where the graph, where the ball landed on the ground, we could not have taken this x equal negative 1 as one of our solutions for this situation. So though it is a solution to the equation here, for the situation, we would actually focus on
where the ball landed, which was 5 meters away from Emmy.
Good that you brought that up.
All right, so let us get into some CSEC questions. Let's look at and see what the questions would actually look like. Now, I hope that you're following and you can see that that math is applicable to real life. I hope you can see this, guys. So let's look at this question, Karimo.
All right, so let's again clear our board a bit.
So we're looking at completing the table below for the function f of x is equal to 3 plus 2x minus x squared. So the function that we're given is f of x is equal to 3 plus 2x minus x squared. And we're asked to complete the table. Now, when x is negative 2, we're asked to find out or
f
y,
of x
or,
or
f
y.
Of, or y coordinates.
Right.
So in order to do this, what do you think we need to do, Karima?
Well, we need to substitute the negative 2 wherever we have x.
So we're substituting negative 2 into our function.
All right, so we're going to quickly do this. So here we have our 3. Now we need to work out what is a positive 2 times a negative 2.
I believe
and that will give me a
negative
4. And here I have a negative 2 that is squared.
And I believe that will give me a positive 4.
But then I also have this sign here, this subtraction sign.
So in fact, it's minus 4.
Minus 4. So here it's 3 minus 4 minus 4, which will now give us a negative 5. For those of you who are having problems with your negative numbers, so we can interpret this as us having 3, we owed 4, and so we use the 3 that we have, pay some of our debt, couldn't pay everything, so we still owed 1. And oh my God, we went and borrowed 4 more.
Yeah, because
so,
you know how time
hard.
Yeah.
So now we owe 5.
All right. So what is happening to f of x when x is 2, Karima?
All right. So it's pretty much a similar routine where we're going to be substituting, in this case, a positive 2 for our values. But you know, can we put in our negative? Oh, it will come both.
Yeah.
All right. Because I wanted to point out something. So when it actually pops in, then we will look at that.
All right.
All right. So now we have 3 plus 4. And here we have our negative 2 squared.
Which is 4.
Or, sorry, no, our positive 2, because that's where we are. Positive 2 squared, which is 4. But we also have a minus sign
So
here.
we're going to be subtracting the 4.
Good.
And automatically I see something.
What did you see?
I see that we're subtracting the same quantity. So I have 4 and I owe 4. So guess what? I can pay off my things. Because I just get 0. So I can pay off all the people that I owe.
But I have this 3 here that I had to start.
Oh yes. So
Right.
so at the end I'll have 3 things still.
So 3, I got 4, and the same 4 that I got, I gave it away. So
Same time.
So I have the 3.
So I have 3 left. So our second coordinate would have been, our second coordinate for our y value would have been 3.
I want to point out something here, Brittany, though. When I look at this equation, as we pointed out earlier, I'm looking here. I remember now, though the equation is written in this form, notice that they're trying to trick us, you know.
Don't.
So it's not looking like ax squared plus bx plus c, so they've jumbled up the terms. But we're smart, not true.
Don't.
So we say that our c value is here, which is 3.
Yes.
Our b value is a positive 2.
Yes.
And my a value is a
Negative
negative
1.
1, which means my graph is...
Is it a happy graph or a sad graph? I think it's sad, you know.
It's sad.
Don't.
It's sad, yeah.
It's sad?
It's sad. It's
Yeah,
frowning.
it's frowning.
So we can actually look now at these numbers on our table, and we can see the frown happening, you know. Watch this. So here we are, -5. Yes,
Yes.
That's way down, right?
Yes.
And we have come up
To 0.
to 0, going up to 3,
Yes.
going up to 4, and then I'm seeing what's happening here now. I'm starting to go back, down,
Oh, gosh.
down. So I
Life
can
gets sad.
actually see with the numbers the curve that is taking place.
Yes, I can see
And
that.
it's important that our students see that. So even when you're filling in the table, you should get a sense of how the graph should look when you plot it on the graph paper.
I think you've seen this question before, you know. So,
Oh my.
no, you realize that we have to draw our graph.
Yes.
So, given the coordinates that we just found a while ago, so CSEC was so nice. You notice?
Yeah.
They pre-filled the graph.
prepared.
Yeah, they
Yes.
pre-filled the graph.
Yes.
So, all we have to do is put in the 2 points that we just found.
All right.
So, let us put in those 2 points.
Ah.
So, our 2 points are now in, and as we stated before,
So
our
that's
graph
-2,
negative
-2,
-2,
-5,
-5,
and +2, 3.
Yes.
Okay.
+3, 3. +3, 3. So as was stated before, our graph is a very sad graph. Now, using the graph, only the graph, we're just going to be looking at the graph. Can you identify the maximum point of f of x?
Of course. Right up
Okay.
there at the vertex.
So right at the vertex, so
Yes.
right where the graph starts to turn downwards and we start to get sad.
You know, we can actually call that a turning point.
Look at that.
Yes.
So right at our turning point, we can
Right.
identify our vertex. And in this case, the coordinate for our vertex is going to be 1, 4.
Ah,
Look at that.
nice. This is so interesting. I'm really enjoying this lesson. I hope our students are too. And I hope they're
Yes.
learning as well.
Now, if it is that we were asked in the second scenario to solve our equation, so when we're solving our equation, what are we doing again, Karima?
All right, so you said that when we're solving, we're looking for when y is equal to 0.
Yes.
And I want to point out something here as well, because if we notice, it said f of x, and sometimes we use y interchangeably.
In f of x.
So if f of x is equal to 3 plus 2x minus x squared, and here we're given that very same 3 plus 2x minus x squared, and we're told now that it is equal to 0, we're basically looking for where f of x is
zero.
equal to
0.
0. And where is that again, Brittany?
Is it called the roots?
It's called the root, and we
The
find it
x-intercept?
on the x-axis,
Yeah.
the x-intercept.
That is what we're looking for. So we're looking for
we
our x-intercept.
So we can actually pick those up from the graph.
Straight away.
Right, so here we have -1, so x is equal to
Negative
-1,
1.
that's one of our roots, and the other one is x equal 3.
Now, we could also go ahead and solve this, right? We could also solve this through factorization, which we had done from before.
You can actually bring that up on the screen.
So, if we solved using factorization, we would still get the same results. Now, let us look at these two graphs. And as was stated before, just by looking at the graph, Karima, we can identify the roots of the graph. Now, as was stated before, the roots of the graph is where where the graph cuts my x-axis. Now let's look at the first graph. As you can see, is this a happy graph or a sad graph?
That's a happy graph.
It's a very happy graph. And is it cutting my x-axis?
It's not cutting it at all, Brittany.
Oh my goodness. So is there a solution for this?
That looks like it has no solution.
So for this particular graph, we have no x-intercepts or any roots.
I didn't know that was possible.
Yes, man. It can have graphs like that.
Oh, what about the second one, though?
Okay, no. Let's look at the second graph. So the second graph is another what type of graph, this, Karima?
Happy graph,
oh,
positive
Lord.
A.
We're just so happy about
Yep.
these things, don't it? So here, we notice that our graph is it how many times is it cutting our x-axis?
It's intercepting it at 1 point.
So it's only cutting our x-axis once. So this 1 point down here is where x is equal to -1.
Oh, so that's one solution.
Yes.
But you know, Brittany, I want to point out something because we have been talking about maximum and minimum. Yes, and in these two, well, the smiling, so the second one actually showed us that minimum, well, both of them had minimum points.
Yes.
Now, we want our students to understand that when we talk about the maximum and the minimum points, we're actually referring to the y value of the vertex, all right? So
yes.
it's the y value that we're speaking to when we talk about the maximum or the minimum
points.
Right.
So, as was shown before, we can have a graph that has two solutions or it intercepts the x-axis twice. We can also have a graph that does not intercept our x-axis.
Yes.
And we can have a curve that touches the x-axis only one time.
Yes.
No.
All right, so I'm sure that our students would have been exposed to factorization. So on screen now, we're basically showing them how through factorization we would have been able to get those very same roots that we got from the previous graphs. Click again for me. Right. Those solution of x being equal to 3 or x being equal to -1. So we're getting the wrap-up signal, and so Brittany, wow, time surely flies when you're having fun.
That is true.
And so we're leaving our students with these two graphs on screen that they should try at home.
So we're
zoom
asking
in
to
on
factorize
that,
these two?
right? So you can solve those on your own time. And of course, we hope that you would have gained something from today's lesson. So as we summarize quickly, today we would have learned that the quadratic graph, or functions rather, can be written as in standard form, ax squared plus bx plus c.
We also realize that we can have a happy or a sad graph if A can be positive or
it's happy,
negative.
right? And if it's negative, the graph is sad.
Okay. The vertex tells you where to find the absolute maximum or minimum value on your graph.
And finally,
our roots or x-intercept is the point where the graph cuts our x-axis.
And there can be one root, two roots, or no roots.